block coordinate descent is a popular method in large-scale optimization, which in every iteration optimizes the problem over a subset of variables, keeping the remaining variables constant. Unfortunately, the fixed points of this method can be arbitrarily far from global optima, even for convex problems, and the class of problems for which BCD provably converges to global optima is currently quite narrow. Yet, BCD methods, known as convex message passing, are state-of-the-art for approximately solving the dual LP relaxation of the map inference problem in computer vision, which is also known as the weighted CSP. Their fixed points may not be global optima, but they are characterized by certain local consistency conditions, namely different forms of arc consistency. Focusing on linear programs, we are going to show that fixed points of BCD are identical to fixed points of another method called Primal-Dual approach, which can provide upper bounds on optimal value of a linear program. It uses constraint propagation to detect infeasibility of complementary slackness conditions in a Primal-Dual loop to iteratively improve a dual solution. This approach is related to the Primal-Dual method in linear programming, and we propose it in our second submission as a generalization of the virtual arc consistency algorithm. In detail, we proposed to replace enforcing arc consistency by general constraint propagation in a system of linear inequalities. Though this is not a BCD method, the fixed points of this approach are also characterized by arc consistency of the active tuples. We show that the Primal-Dual approach with a specific kind of constraint propagation and BCD have identical fixed points, which unfortunately may not be optima, but only provide an upper bound on the optimal value. We precisely define the propagation rule and show that its properties resemble other already known propagators such as arc consistency closure propagator. Consequently, BCD on any LP in any form with any blocks of variables in fact implicitly performs the proposed propagation rule. Using these results, the question if a given linear program is exactly solvable by BCD can be translated into the question if feasibility of a certain system of linear inequalities is decidable by a precisely defined propagation rule. Thus, the results characterize the classes of LPs optimally solvable by BCD by tools of constraint programming, and also characterize the types of local minima in BCD by local consistency conditions. We will now describe both methods in detail on a linear program in general form and then state our results formally. We consider the Primal-Dual pair shown in equation 1. We will call the problem on the left primal and the problem on the right dual. Note that any y feasible for the dual is an upper bound on the common optimal value of the pair. For both considered methods, we suppose that an initial dual feasible solution y is provided, which will be iteratively improved. In addition, we assume that there is a finite collection of subsets B, which contains subsets of the set M. This collection B defines the blocks of dual variables, along which we will update in block coordinate descent, and also defines which subsets of primal constraints will be used in propagation. We will now describe how block coordinate descent is applied on the dual LP. For convenience of further explanation, we reformulate optimization of the dual LP as minimizing the shown extended valued function f, which encodes both the dual objective and the constraints. BCD initialized in a feasible dual solution y chooses a single block from the set of blocks and updates the current point y so that equation 2 is satisfied. Symbol yb denotes the components of vector y which are in the block b, and symbol y minus b denotes the remaining components. Informally, the block of variables b should be at optimum while keeping the other components of y fixed. The choice of block and the update are repeated unless a termination condition is satisfied. It was recently proposed that the optimizer should be chosen from the relative interior of the set of optimizers as indicated in equation 3. This is called the relative interior rule and it can be shown not to be worse than any other exact update rule. We will now overview the main properties of the fixed points of BCD. We say the point y feasible to the dual is a local minimum of f with respect to set of blocks B if condition 2 holds for each block. It is an interior local minimum if condition 3 holds for each block. Clearly, interior local minima are fixed points of BCD with relative interior rule. There also exists a third kind of local minimum, called pre-interior local minimum. The exact definition of these points is technical, but they can be precisely characterized as points from which no sequence of updates 2 or 3 can improve the objective. Also, after a finite number of updates 3 applied from a pre-interior local minimum, we attain an interior local minimum. On the other hand, points which are not pre-interior local minima can be improved by a finite number of block coordinate updates. We will now point our attention to the second method, namely Primal-Dual approach. Recall the previously shown Primal-Dual pair. Let us define the set Ky as the index set of dual constraints active at point y. It holds by the well-known complementary slackness theorem that a dual feasible point y is optimal if and only if system 5 is feasible. By Farkas lemma, it holds that system 5 is infeasible if and only if system 6 is feasible. We remark that any vector y bar satisfying system 6 certifies infeasibility of system 5 and also constitutes an improving direction for the dual from the current point y. In other words, if y is not optimal, then there always exists an improving direction along which we can perform a step of non-zero length to update the current y. After the update, the objective improves by condition 6a. We proposed in our second submission to apply certain problem-dependent propagation rules on system 5 in order to possibly detect its infeasibility, and, whenever infeasibility is detected, construct the certificate of infeasibility y bar and improve the current point. The whole Primal-Dual approach with constraint propagation therefore proceeds as follows. First, we obtain an initial dual feasible solution y. This point will be iteratively improved as follows. Based on the current y, we create the previously shown system 5 called complementary slackness conditions. We apply predefined constraint propagation rules on the system, and if the rules do not detect infeasibility, then the conditions are suspected of being feasible. In other words, the current y is suspected of being optimal and the algorithm terminates. Note that the returned y may not be optimal if the propagation rules are refutation incomplete. Otherwise, if the propagation rules decide that the conditions are infeasible, we are able to take the propagation rules in an anti-chronological order to construct the dual improving direction y bar. We calculate a non-zero step size for updating the current solution while improving the objective. By this update, we obtain a new estimate for the optimal solution and repeat. This approach subsumes, for example, the virtual R consistency algorithm if we applied it to the basic LP relaxation of a weighted CSP and constraint propagation corresponded to R consistency of CSP defined by the active tuples. In general, constraint propagation in a system of linear inequalities and equalities can of course be done in many ways, and the Primal-Dual approach can be applied to any such rule. However, we consider here a single particular propagation rule which is applicable to any linear program. In detail, we will choose a subset of inequalities and infer which hold with equality. For the previously shown system of complementary slackness conditions, where k is initialized as ky, this corresponds to choosing a block of primal constraints B and finding all indices k from the set k such that system 8 implies that xk equals 0. Then we remove such indices from the set k. Notice that the system 8 is identical to 7, except that it contains only a subset of the primal equality constraints. We repeatedly make the set k smaller until it doesn't change or system 8 is infeasible for subset B. See that if system 8 is infeasible for some B, then this also implies that system 7 is infeasible. Clearly, this method corresponds to deciding which of the inequalities needs value with equality. We will now analyze the propagation algorithm in detail. We remark that system 8 on this slide is identical to the system with a subset of primal constraints which was considered before. We say that set K is B consistent if for every K in K, system 8 doesn't imply that xk equals 0. Also, we define for a collection of subsets calligraphic B that a set K is B consistent if it is B consistent for each element in the collection. Our motivation for introducing B consistency is to present analogy with R consistency, as we shall see later. It can be shown that the union of two B-consistent sets is again a B-consistent set. Therefore, B-consistent sets form a joint similatris with respect to inclusion. Additionally, this implies that for any set K, either there is no B-consistent subset of K, or there exists the unique maximal B-consistent subset. This allows us to define the map PB. PBK is the maximal B-consistent subset of K if the set K has a B-consistent subset. Otherwise, if K has no B-consistent subset, PBK equals a special contradiction sign. This mapping will be called the propagator. We will now proceed to define the propagation algorithm which enforces this kind of local consistency. The algorithm is defined by a collection B of subsets and is given K, which is a subset of M. The propagation algorithm proceeds by finding a block such that applying the propagator on K changes its current value and updates K. These updates are repeated until no such block exists or K equals contradiction. Eventually, after a finite number of steps, K is returned. It can be shown that the result of the propagation algorithm is independent of the choice of blocks P, which allows us to denote the result of the propagation algorithm as PBK with calligraphic P. It is possible to prove that if K has a B-consistent subset, then the propagation algorithm returns the maximal B-consistent subset. So, it is easy to see that the propagation algorithm is refutation incomplete in general, but if the algorithm returns contradiction, then the original system is infeasible. In such case, it is possible to construct the previously mentioned infeasibility certificate, respectively improving direction, using the entire chronological order of the blocks B as they were applied in the propagation algorithm. We give a description of this procedure in the paper, but it is not necessary for the following parts of this talk. Finally, the propagator and the propagation algorithm have properties of a closure operator, which resembles other already known propagators and local consistencies, such as arc consistency closure. Also, the fact that the union of two B-consistent sets is a B-consistent set can be linked to so-called stability under union of locally consistent problems. We will now precisely state the relation between block coordinate descent and constraint propagation. If y is a feasible point for the dual, then y is a local minimum with respect to b if and only if the propagator does not detect inconsistency for each of the blocks individually. Y is an interior local minimum if and only if the propagation algorithm cannot perform any more propagation, that is, the set ky given by active dual constraints is b consistent. Also, y is a pre-interior local minimum if and only if the propagation algorithm doesn't detect contradiction. The theorem characterizes the previously introduced types of local minima in block coordinate descent by local consistency conditions. It also shows that BCD with relative interior rule cannot improve the fixed points of the Primal-Dual approach based on propagation and vice versa. This yields the following corollary. For a fixed optimization problem and a fixed set of blocks, the following are equivalent. First, for all feasible points y of the dual, if the previously shown system given by complementary slackness conditions is not feasible, then the propagation algorithm detects it. This, in fact, means that the algorithm is refutation complete. Second, any interior local minimum y of the dual with respect to B is a global optimum. As a consequence, deciding whether BCD fixed points are global minima for a given class of LPs can be reformulated as the question whether constraint propagation decides feasibility of a certain class of linear inequalities. This tight connection may provide theoretical ground for analysis of BCD in terms of constraint propagation. Moreover, it may result in newly discovered classes of problems optimally solvable by BCD, or better designed for choices of blocks of variables so that the propagation is more effective and BCD may reach better local optima. Even though the shown statements are proved for the standard LP formulation showed previously, we've also discussed in the paper that the propagation algorithm can be generalized to LPs in any form. In detail, BCD in the dual for a given set of blocks corresponds to propagating which primal constraints given by complementary slackness should be active and which inactive, while inferring only from subsets of the constraints given by the blocks. Therefore, the previous results hold for any LP in any form with any blocks of variables. It was observed that transformations of linear programs which preserve all global minima may not preserve interior local minima. Such transformations include, for example, adding or removing redundant constraints. The connection of BCD and constraint propagation precisely explains this, as such changes significantly affect the behavior of the propagation algorithm. The proposed kind of propagation subsumes a number of already existing algorithms which can now be shown to be equivalent to block coordinate descent with relative interior rule. As already mentioned, this kind of propagation subsumes the virtual R consistency algorithm, respectively the closely related augmenting duck algorithm. These algorithms were already known to have the same fixed points as a block coordinate descent method known as max sum diffusion. Our results therefore generalize this connection. If we formulated minimization of a convex piecewise affine function as a linear program, then the proposed propagation is equivalent to the sand relaxation technique. An algorithm which also performs such propagation was specifically designed for the LP relaxation of weighted maxad in our second submission to CP2020. Now it is shown to have equivalent fixed points as BCD with relative interior rule on the dual LP. Lastly, if we consider the LP relaxation of SAT and wanted to decide its satisfiability, then if the dual is initialized at 0, the proposed propagation algorithm corresponds to unit propagation. Additionally, since BCD algorithms max sum diffusion and TRWS satisfy the relative interior rule, their fixed point conditions are equivalent to our local consistency condition if applied to the corresponding LPs with certain specific set of blocks of variables. In fact, there also exist other convex message passing algorithms whose fixed points are pre-interior local minima and which can therefore be also characterized by the shown local consistency condition. The practical impact of these results is mainly focused on approximately optimizing challenging large-scale LPs which are not solvable by off-the-shelf LP solvers. Propagation algorithms subsumed by the proposed one were previously derived ad hoc for specific LPs where they provided useful solutions which are often close to global optima. We believe that presenting all of these algorithms in a single framework may simplify design of similar methods in the future.